Alright guys, let's do number 49. Let's get started. Because the Earth rotates about its axis. A point on the equator experiences centripetal acceleration of that, whereas a point of the poles experiences no acceleration. Alright, so let's draw a sphere. Oh my god. Good enough. Anyway, let's try again. Good enough. Anyway. So here's the Earth. And what I'm going to do is at the equator, when this thing is rotating, as the Earth rotates, you're going to have mg, and then you're going to have the normal force as the forces. So mg minus the normal force equals mb squared over the radius of the Earth. If there is no normal force holding you in contact with it, and you just happen to be rotating with the ground, then b is going to be the square root of g over r. The radius of the Earth is going to be 6.3. Where's my calculator? I don't know if I have that stored here. Oh no, I don't. Okay, 178 or something kilometers. Let me look this value up. All right, cool. Wait. So the radius of the Earth is 6.378 kilometers. So the centripetal acceleration is going to be a v squared over r. But what I'm going to do is I'm going to take the 2 pi r divided by the time, and that time specifically is going to be 24 hours. So I'm going to put that in there. I'm going to store everything in there. 6.378. That's the radius. 24. I know this is not part of the problem, but it's good to kind of understand where these concepts here. So all right, so 2 pi r divided by t is going to be the velocity. So I got the velocity at 463.82 meters per second. Presuming I did. So notice that I put all this together, and I'm going to take the v squared divided by the r, and I'm going to store that into the alpha radius. And conveniently, once you plug this formula in there, then you would get the radius, the centripetal acceleration would have to be 0.0337 meters per second squared. It's as exactly as the problem states. Show that the equator of the gravitational force on an object must exceed the normal force required for the object. So anyways, regardless of this, once you have v, must exceed the normal force required of the object. So let's just say that the normal force is 0 here. and show that the gravitational force, I don't know what they want. Do they give the mass of the object? No, they do not. So that would be all I know is that this right here, if this is going to be the normal force, this would have to be the minimum value of the velocity, I believe. Because the more v squared over r would be g. I guess we can just write this, I guess. G equals v squared over r. 9.8 meters per second square. This would have to be greater than 0.033 meters per second square. So this would have to be greater. So let's just say that mg, whatever this is, would have to be greater than v square over r. All right, so I guess that's going to be part A. I don't know what they want. All right, so let's do part B. We're almost done anyways. What is the apparent weight of the equator and at the poles of the person having mg? Well, if the velocity is 0 right at the top, or when the radius is 0 and the velocity is big, I guess, or let's just say that the v is 0, or let's just say that, you know, what is the apparent weight of at the poles? Okay, well, that's just going to be mg. That's just going to be the mass here is going to be 75 kilograms. So the weight here would have to be the mg minus v squared over r. This is going to be the weight. It's all going to be dependent on that. But we're going to let this be 0. We're going to let the centripetal acceleration be 0. And let's just say that mg, the weight here, would have to be, so remember, the weight here is going to be the mass times gravity. And that's going to be 735 newtons. Part C, the weight here is going to be equal to the mg minus v squared over r. The values might look a little different from the book, but this should be approximately, is that right? Mg minus, yeah, it looks like it is. Let me look at the back of the solution menu here. So the answer here is going to be 732 newtons. All right, so that's going to be the weight, or 0.47 newtons. I'm just going to leave it at that. So this is going to be 47 newtons. All right, we're done.